Imagine for a moment that every time you walked from your kitchen to your living room, you didn't take one path, you took every possible path. The straight line through the doorway, sure, but also the route through the wall, the detour around the moon, a side trip to Mars, a quick loop through the next galaxy, and somehow all of them simultaneously. It sounds absurd. It sounds like science fiction. But this is not a metaphor, and it is not a thought experiment. According to one of the most successful theories in the history of science, this is exactly what an electron does. Every single time it moves the width of a single atom. And the man who first dared to take this idea seriously was Richard Feynman. Most of us, when we first learn physics, are taught a comfortable story. A ball thrown into the air follows a single, smooth, predictable arc. Light travels in a straight line until it hits something. Particles have positions, they have velocities, and they go from point A to point B by travelling the path between them. It is an elegant picture, and for the world of bridges and baseballs and rockets to the moon, it works beautifully. But underneath that picture, at the level of electrons and photons, and the things that actually make up everything you have ever touched, the story turns out to be something stranger and far more interesting. It turns out that what we call the path of a particle is not really a path at all. It is a kind of vote, taken across an infinite committee of possibilities, with the universe quietly tallying the results before it lets you see the answer. To understand how Feynman arrived at this picture, we have to go back further than him, all the way to the 17th century, to a French lawyer named Pierre de Fermat. Fermat was not a professional scientist. He was a hobbyist who happened to be a genius. And one of the things he noticed about light was almost mystical. Light, when it travels through air and then water, or through a lens, or through any medium where its speed changes, always seems to take the path that gets it from start to finish in the least amount of time. Not the shortest path, not the most direct path, the fastest one. Which is a very strange thing for a beam of light to know in advance. How does the light know, when it leaves a candle, which direction will turn out to be the quickest route to your eye? It almost looks as though the light has surveyed every option, calculated each travel time, and intelligently picked the winner. Centuries passed, and physicists realised that Fermat's strange rule was not just a quirk of light. It was a glimpse of something deeper. They generalised it into something called the principle of least action. Every physical system, from a falling apple to an orbiting planet to a swinging pendulum, behaves as though it is minimising a particular quantity called the action over the course of its motion. The principle of least action is one of the most beautiful ideas in classical physics. It also feels, philosophically, a little uncomfortable. Because how does a planet, halfway through its orbit, know that the path it is currently on will turn out, in retrospect, to have the smallest action? It is as though the universe is solving an optimization problem, and we are watching only the answer. For a long time, physicists treated this discomfort as a mathematical curiosity, a nice piece of bookkeeping. They moved on. And then quantum mechanics arrived in the 1920s and broke everything. Suddenly, particles did not have definite positions until you measured them. Suddenly, probability replaced certainty. Suddenly, an electron, asked to go through one of two slits, refused to commit and instead behaved as though it had gone through both. The old picture of a single, well-defined trajectory was finished. And into this strange new world walked a young, restless, brilliant graduate student at Princeton who had just one question. If the principle of least action is true in the everyday world, and if the everyday world is built out of quantum particles, then what is the principle of least action really doing underneath? Feynman's answer, when he finally arrived at it in 1948, was breathtaking. He said this: The reason a particle appears to follow the path of least action is not because it intelligently selects that path. It is because it takes every path, every single one. The straight line, of course, but also the wiggly ones, the looping ones, the ones that double back on themselves, the ones that go to the Andromeda galaxy and come home. All of them. Each path the particle takes carries with it a small mathematical object, a kind of rotating clock hand called a phase. And to find out what the particle actually does, you take all of these rotating clock hands from every possible path and you add them up. That sum over an infinite number of histories is what Feynman called the path integral. It is also the reason this whole framework is sometimes called the sum over histories. And here is where the magic happens. Most of those infinite paths, the wild ones, the ones that loop through Mars or zigzag through your bathroom, have phases that point in essentially random directions. When you add up a forest of clock hands all pointing every which way, they cancel each other out almost perfectly. They contribute nothing. The only paths that survive the summation, the only paths whose phases line up and reinforce each other instead of cancelling, are the paths very close to the classical path of least action. Which is why in the everyday world, you only ever see the classical path. Not because the others did not happen, because the others happened and then erased themselves through interference. The classical world is what is left over when the quantum world finishes voting. If you have ever heard of the double slit experiment, this is the moment to think about it again, because the path integral makes it almost obvious. A particle goes through two slits. It interferes with itself. Why? Because there are two paths, one through each slit, and you add them. Now imagine 3 slits. You add 3 paths. 100 slits. You add 100 paths. Now imagine you remove the wall entirely. Every point in space is, effectively, an open slit. The particle goes through all of them. The interference pattern is not some weird exception. It is the rule. The classical trajectory, the smooth, straight line we are taught in school, is the exception. It is the special case that emerges only when the alternatives drown each other out. Now here is the part that I think deserves a moment of stillness. When you sit with this idea, really sit with it, you start to realize what it is saying about the universe at the deepest level. It is saying that reality, at its core, does not compute things sequentially. It does not pick a path and then evaluate it. It evaluates every path in parallel, in a single, timeless act. And what we experience as motion, as causation, as one thing leading to the next, is the residue of an enormous, hidden, parallel calculation. The universe, in this picture, is not a story being told one sentence at a time. It is a story whose every possible draft is being written at once, and we live inside the version where the drafts agree. This is not just philosophy. The path integral is the workhorse of modern physics. Quantum field theory, the framework that describes electrons, photons, quarks, and every fundamental particle we know, is built on path integrals. The Feynman diagrams you have probably seen on physics blogs, those squiggly lines that look like cartoons of particles bumping into each other, those are not pictures of what particles actually do. Each diagram is one term in a sum over all possible histories. Quantum electrodynamics, the most precisely tested theory humans have ever produced, accurate to 12 decimal places, is essentially a path integral, evaluated very, very carefully. The semiconductors in your phone, the lasers in your fiber optics, the design of every quantum computer being built today, all of them rest, ultimately, on this 75-year-old idea that the universe runs every calculation at once. So is it real? Is the universe genuinely taking every path? Or is the path integral just a fantastically clever piece of mathematics that happens to give us the right answers? This is one of the great open questions in the foundations of physics. And I want to be honest with you, we do not know. Some physicists, like David Deutsch, take the path integral as evidence that we live in a multiverse, where every possible history actually happens in some branch of reality. Others see the formalism as a powerful tool with no claim on metaphysics. Feynman himself was famously cautious. He said, more or less, that he did not know what was really going on, only that this was the cleanest way he had found to predict what we measure. And there is a kind of intellectual honesty in that position which I deeply respect. The math is not the territory. The map can be perfect without telling you what the land underneath is made of. But whatever the right interpretation turns out to be, one thing is certain. The next time you look at your hand, or at the screen you are watching this on, or at the stars in the night sky, you are seeing the surface of an enormous hidden process. Underneath every photon that reaches your eye is a sum over infinite paths. Underneath every electron in every atom of your body is an entire library of histories, most of which cancelled each other out before you ever noticed. The universe is, in a very real sense, computing itself, all at once, all the time. And we are living inside the answer. If this kind of thinking is the kind of thinking you came here for, the slow, careful, grown-up examination of how the world actually works, then please consider subscribing. There is so much more to talk about. The mysteries of quantum field theory, the deep questions about time and causality, the ongoing arguments about what quantum mechanics is really telling us. I would love to keep walking through these ideas with you, one careful step at a time. Until then, take care, stay curious, and remember that every path you didn't take today, in some small mathematical sense, was still part of how you got here.